the first Bragg diffraction peak is having an 2 theta value of 44.53. As previously discussed, we can note the value over here. It is 44.53 degrees. And the second Bragg diffraction peak is occurring at an angle of 51.89 degrees. And the third diffraction peak is arising at a value of 76.45 degrees. Now represent the 2 theta values for various Bragg diffraction peaks as obtained from the pattern. We can see that the first Bragg diffraction peak is occurring for twice the Bragg angle of 44.53 degrees, and the second Bragg diffraction peak is occurring at an angle of 2 theta equal to 51.89 degrees, and the third diffraction peak is occurring at an angle of 76.45 degrees, and fourth peak at an angle of 93.01 degrees, and the fifth peak at an angle of 2 theta equal to 98.51 degrees, and the sixth Bragg diffraction peak is occurring at an angle of 2 theta equal to 122.12 degrees. Now after 2 theta, find out theta value. That is, now the theta values or the glancing angles will become, for the first peak it is 22.265, for the second peak it is 25.945, for the third peak it is 38.225, and for the fourth peak it is 46.505, and for the fifth diffraction peak it is 49.255, and for the sixth diffraction peak it is 61.06. These are the glancing angles or the angles of diffraction from various parallel planes of atoms. Now after sin theta, find out sin square theta for all these values. Find sin theta and sin square theta. Now this here in this chart, 0.144 is now the least value of sin square theta compared to all the Bragg diffraction peaks. You can observe here. Now sin square theta by sin square theta minimum, that is dividing all these values by the minimum value, that is 0.144, we will get as 1, 1.33, 2.66, 3.63, 3.986 and 5.32 respectively on division. Now multiply this sin square theta by sin square theta minimum, this ratio, by a factor 3. If you multiply, we are getting the values for the first Bragg diffraction peak as 3, for the second Bragg diffraction peak as 3.987, and for the third Bragg diffraction peak as 7.98, and for fourth Bragg diffraction peak it is 10.96, and for the fifth Bragg diffraction peak it is 11.958, and for the sixth Bragg diffraction peak it is 15.96. Now rounding off to the nearest digits, we get this h square plus k square value as, we should round off this value to the nearest decimal, we will get it as 3, 3.987 can be rounded off to 4, 7.98 here can be rounded off to 8, 10.96 can be rounded off to 11, and 11.958 can be rounded off to 12, 15.96 can be rounded off to 16. These are now the h square plus k square plus L square values for this Bragg diffraction peaks here. Now by using the standard chart and these values of various h square plus k square plus L square, we will find the Miller indices values HKL. Now how it can be done? Now we will see the first peak here. The first peak is having a h square plus k square value of 3. Now here we have provided a selection rule chart. Now if you look at the value of h square plus k square plus L square is 3, the corresponding Miller indices are 1, 1, 1. So represent the Miller indices here as for 3 as 1, 1, 1. Similarly, for the second Bragg diffraction peak, the h square plus k square plus L square value is 4. So again, moving to the selection rule chart, we can see that this value of 4 is arriving for the HKL values of 200. So I have put it over here 200. Similarly, for 8, h square plus k square plus L square value of 8, the corresponding Miller indices are 220, and for 11 it is 311. This can be seen here. For 8 it is 220, for 11 it is 311, and similarly for 12 it is 222. This is again observed here. For 12 it is 222, and for h square plus k square plus L square value of 16, that is for the last diffraction peak, the HKL value is 400. It is observed here 400. Right. Now we can find the lattice constant. To find the lattice constant, what we'll do is, the formula is being given, A equal to lambda by sin theta into root over h square plus k square plus L square. So for each and every Bragg diffraction peak, find the corresponding lattice constant. So on substituting the value of sin theta for the first Bragg diffraction peak and h square plus k square plus L square value here, we got the value as 7.0406 for the first Bragg diffraction peak. For the second peak, we obtained in a similar fashion as 7.043. For the third Bragg diffraction peak, the calculated lattice constant is 7.0282. From the fourth Bragg diffraction peak, the calculated lattice constant is 7.044. And from the fifth Bragg's X-ray diffraction peak, the calculated lattice constant is 7.0406. And for the final diffraction peak, the calculated lattice constant is 7.0427. Now the average lattice constant of the crystalline material can be calculated to be around 7.04. This is the average lattice constant of the material. Next, we have to also determine what is the crystalline phase. So how to determine the crystalline phase? Here, if you take the cubic, we have in a cubic, because here we are multiplying by 3, we can see it is a cubic lattice. For a cubic lattice, there are 3 different kinds of lattices, that is simple cubic, BCC and FCC. So among these 3, what could be the possibility? So if we go to the selection rule chart, here we can see that for a simple cubic lattice, all parallel planes of atoms are possible. All these Miller indices are possible for simple cubic. But simple cubic is also a very rare element to be, rare crystalline phase to be formed. Only polonium is the only material that exhibits simple cubic lattice. No other material exhibits simple cubic. So we can eliminate this. So only the possibility is in between either BCC or an FCC. So the shown crystalline phase can be either BCC or FCC, because simple cubic is only possible for polonium, and also in a simple cubic lattice, all the X-ray reflections happen from all these possible planes. So based on that conclusion, we only consider either it should be a BCC or FCC lattice. How to choose that? We can observe here that the 111 reflection, the reflection from 111 plane is occurring only in FCC but will not occur in a BCC lattice. Also, if you take the 311 reflection from 311 plane, this reflection from 311 plane is also occurring for FCC lattice but does not occur for BCC lattice. And all other possibilities are there. If you take 200 from 200, in both FCC lattice and BCC lattice reflections occur. For 220, in both BCC and FCC reflections occur. Similarly, for 222 also, for BCC and FCC, Bragg reflections can occur. Also in 440 also, Bragg reflections can occur for both BCC lattice and FCC lattice. But these two reflections, that is a 111 and that is 111 reflection from 111 plane and reflections from 311 plane, can only happen for FCC. So the crystalline phase shown in the earlier figure should be an FCC lattice.